in this work, what we have done is that we uh, basically extracted all the traffic data for the entire interstate network of Florida. And we got the information like traffic variation overall, like a number of traffic that is moving for different interstate network and over different times. And then we also have extracted the information like the hurricane rainfall time, and also a few other information like the population over different county. So all this information we collected from different sources, and mainly the traffic data. It's very robust and dynamic. We collected it from the RETIS, and this data belongs to the hurricane evacuation period of Hurricane Irma. So once we got the data, then we did some processing to make it like a input ready for our dynamic traffic model, dynamic graph convolution model. So after the processing, we make sure that we also did some validation to make sure that the data is making sense, because like in a model, if we provide the wrong data or any garbage information, that the model will also perform very poorly. So we did rigorous validation on the data after processing, and then use that data to train the model. Now, the training part was tricky because it's a big network, and we cannot like have lots of data during evacuation period, because evacuation happens like maybe only for a week at best. So we have a very small amount of data. And with that data, we cannot train the entire model because it's a big model, and it needs like a significant amount of data to train it correctly. So then what we did is basically we come up with a different strategy where we can learn the network and network dynamics from the regular period, because in general, the network connections and how the traffic is moving in the network and how those traffic at different points are basically affecting each other. This information are very generic, right? So what we can do is that we can use the regular period data and train the model to understand all those dynamics. So once you learn all those dynamics, those are like a generic information. Now you just need to pass this generic information to a model, and then that model can be tuned again with the evacuation data, and that will be able to get both benefit from both work. It knows how the traffic dynamics works, and then it will also know how the demand is varying over the evacuation period. Now, combine these two things, two information together, and come up with a new model, which is, we call it transfer learned dynamic graph convolution model. And that model will predict the future traffic, and it has the understanding of both the information about the network dynamics and also the information that is coming from the evacuation period, like the number of population under evacuation, where was the landfall, what is the distance from the landfall to a evacuation zone. So all this information are already extracted from different sources. So this information, these two information, like network information, network dynamic information, and the evacuation demand information, these two information fused together, and then this information was fed into our transfer learned model to get the final output for evacuation traffic for future 6 hours. Like so, if we want to get the information, we get it at a 6 hours. So if it's at 9 a.m., then we can know like what will be the traffic condition over the next 6 hours. So this is what we actually did in our study. Okay. So now I'm going to give an overview of our method. So I'll give you a walkthrough of the code and also the method that we developed for this study. So first, in the as you can see the methodology section, we have the overall like the overview about our model that we have developed. So here there are a few things. First, like this is a dynamic graph convolution model. So that means like there will be like a multiple items that we need to add. First thing is that like the network that is dynamically changing over time. So when we say like the network dynamically changing over time, what does it mean is that, so in a network, we have like a multiple nodes, and in between each node, we'll have the distance and the travel time. Okay. So when we say the network will be changing, that means our travel time for different nodes will be changing. Okay. So in the first part, what we did is basically we created that dynamic graph where we have the adjacency matrix, which will give you the information about like the connection between different point of the network. And then inside that adjacency matrix, we embedded the travel time information, like a travel time between two different points. And that information is changing over the time. And this is what we see as a graph, dynamic graph. As you can see here, notation G, and it's showing it's changing over different time. And in our model, we need to learn this behavior and how the network is behaving over different time. To learn that, we introduce this parameter, which is WGC. This will learn this network behavior. So now once you learn all these things, then what we're going to do is that we'll insert the information about like how the traffic, basically the number of people that is traveling, like a total count of people that is traveling over total vehicle actually that is traveling for different point, that information embedded in each of the node of that network. So that will be also changing over different time. So now, finally, what we do is that basically we learn all these items together, and this is introduced as an intrinsic hidden layer. Okay. So basically, in this first layer, what we are going to do, we are going to learn the dynamic behavior in the network, along with how the traffic is changing over different point of the network. And finally, this information will be embedded as a intrinsic hidden layer in our model. And finally, so this is now all this information are basically spatial, like different points, the travel time between different points, connection between different points, how one point is, what traffic at a given point in the network is influencing the other surrounding nodes or points. So all these things are learned here. So once you learn this intrinsic behavior, now another thing we need to know is that so this is changing especially like here is changing especially that you understand, but also over time, like over different hours, the traffic will also change. So there is also temporal variation in the traffic. So now to learn this temporal variation, the best possible way is to basically apply a model that is more familiar with the time series behavior. And here we use an LSTM model. So basically our intrinsic hidden information about the network information is passed through a LSTM layer. And finally, this LSTM layer learn the temporal behavior as well. And finally, we get the final output. And that gives us the information about prediction about the future traffic over different time steps. So for our case, we tried with the 6 hour, but this is parameterized, right? So you can say, give me forecast for 10 hours, give me forecast for 12 hours. So all these things can be passed, and it will be act accordingly to give you the future forecast according to that information. So this is basically our entire dynamic graph convolutional LSTM model. There is two parts. One is basically just to learn the intrinsic behavior of the network, just how network is connected, how the special variation in traffic happening, how they are influencing each other. And then once we learn that, then the temporal layer, which will give you the flexibility to learn the temporal correlation over different time period. So this is the core model for this study. So now, since we know the method, now let's see how we implemented this study. So I'll give a walkthrough over the code. So how we did that. So let me just. So first is basically only the inputs. So what type of input the code takes. So there are multiple inputs. Since we already said, first we train the model using the regular period data. So here we already have the process data in a array as an array. So to this, why we did that? Because the data is very vast, and we cannot directly consume the data as a data frame. That will take lots of memory. So we converted into a like a more smaller version, and that array is basically a good way to do that. And then we also have the information about the network. So network, we provide the network information as a adjacency matrix. So this matrix will give you the connection between different nodes of the network. And when I say nodes, that's basically these nodes are the detector that was already deployed into different location of the network. So those are basically my data collection points. So that's give you the adjacency matrix. And all these things basically have some high data processing requirements. So you have a separate paper for that as well. And then, so now, depending on like whether you want to use the transfer learn model, you can either enable the transfer learn or disable the transfer learn. So if you enable the transfer learn, then you have to provide the link, like where is your model is saved. So the location where you save the previous model, you have to provide the information. So for our case, we're not currently looking into transfer learn. We're just looking into the dynamic graph convolution LSTM model. So that will be my focus. And then we need to know like what are the features that we will be passing for the models. So we have the regular feature and evacuation feature. And all the detail about the feature is already written in the paper. And I also have a mapping here just to give you an idea, like what are the feature. Like for example, like there are features like now total traffic, total population mean over different days that were under evacuation. Then we have information like what are the traffic, like here we see there is a standard deviation in traffic and then actual traffic. So all this information are already processed and kept in this file. Just need to assign like which information we are going to use. So for our case, I'm assigning like these are the information that we want to use for regular period. Uh, okay, and then apart from that, we have some model-related feature like number of input nodes, hidden nodes, number of layer, and how many training step or epoch that we are going to use to train our model. So all these things are passed through this config. And then we also can say whether we want to save the model because it's a first model. So we need to save it and then we can use it later for transfer learning. So that's why I enable like a save model true. And then finally, I provided an output directory where I will have this model ready. So these are the main input to the model. So then the model is basically this main function this is the entry point for the model, and it will call the model based on the input that you have provided. So since for my case, it's mainly a mainly I'm getting the initial model, dynamic traffic assignment, dynamic graph convolution LSTM. So I'm following this part, like the first part, first block is basically for the transfer learn model. Like if you want to train the transfer learn model, then you can use that. Or if you want to just start initially to go with your dynamic graph convolution LSTM model, then you have to use this block. So now in this block, again, like we have the all the features loaded as in NumPy. So I get this feature, and then I get the feature size and etc. And then I have the like what are the feature, what are the exact variable that I'm going to use. So I already passed it through config. So all these things already got from the config, and then it will use the like a training and validation. So for this demonstration, I use a very small sample. So that's why I'm manually passing the train and valid portion. But we also have a config to pass that information, like how much portion will be used for testing and validation. So now finally, once you set up everything, now the only thing left is basically call the model. So this is our graph convolution LSTM model. I can show you like how the model look like. So now if I go inside that model, so now this is the graph convolution model. Basically, it consumes all the config that you have passed, and then it has that uh, um, forward pass, like where you do all the mathematics, like basically all the multiplication and all the summation that was designed in the study. So all these things are happening here. And as we know, as you can see that you also calling the LSTM model, like once the learning for the first part, learning for the special temporal, special features and special correlation is done, then we pass this information through an LSTM to learn the temporal variation. So once you get the temporal variation, finally, we use the temporal variation to convert it into our output, desired output, the way that we want. We convert it, and finally, we use our output to check like how the forecast look like. Okay, so that means here are two blocks. One is just the graph convolution block, the first one, which is doing the math for the first block, which is doing the math for the special learning the special correlation and special features. So once you learn that, then pass this information to your LSTM model here, LSTM model. So once you pass the LSTM model, it will learn your temporal correlation, and finally you will get the final output. And here we do some mathematics here as well to understand like what will be the desired output based on the time step we want. So if we want like a 6 hour, then it will do process that way to give us like a next 6 hour information. If we want to know 10 hour, then it will process the information in a way so that we know what is the 10 hour information, forecasted traffic for next 10 hour. So now this is the model overview. Now in the training process, we have to like understand like we have to pass this model through a optimizer, and then optimizer will train the model, tune all the parameters like this. There are weight for graph convolution. You see the WT weight for graph convolution, and the LSTM also have its own weight. So we need to fix those weight through an optimizer, and our optimizer is basically we use Adam optimizer. Now, since we saw the graph and we saw the model, so we can go back to the main function, and here you can see the model we know. Now we pass this model to our training process, and we can go back here and yeah, so this is basically the training process happening here. And we use then Adam optimizer to train the model, and the learning rate and everything we also parameterize through our config. So all the model and all the input data will be passed through this layer, this function, and it will train the model and will try to squeeze the loss function. And our loss function is basically the um, mean square root error. So it will try to minimize that loss function, square root error. So and then once we know that yes, it's have learned the parameter correctly and the parameter set it up, and the model test values are looking good, then we know the model has trained well and it has fixed the parameter. Now, once you fix the parameter, so once that is done, then we can also check the loss function, like if it's how the loss function look like, either from the training side where you'll see the how the loss function is basically, as I said, like it's a mean square root of error. So so that means it will show you whether it's trying to minimize the error or not. So once you call this function, then you'll see this kind of thing, like how the loss function is changing, how the training loss, validation loss is changing. So it's supposed to reduce this loss function, and that's what is happening here. So since we are using a very toy problem, and so that's why like I reduce the number of step to only 4. So that's why you only 3. So that's why you see the loss function also decreasing, but still there are a lot of things to decrease. And overall, it takes around 100 iteration to finally fix the weights. So now once the training is done, you see that your training loss has not changing anymore. It's basically remaining the same thing again and again. So then you realize, okay, now my model has fixed and my weights are already trained correctly. Now I can use the model to do my test and forecast. So once you train the model, so another thing we do is basically to make it like a production ready. So we usually save the model. So here we have the parameter. I said like save the model. So we're not using transfer learn. We're just using a regular model. So then the regular model will be getting saved as a regular model.pth and the output directory. So I already saved the model some in my output directory, and we can use this model either for testing or to predict the traffic for regular period, or which is the next step to for evacuation traffic prediction. So now to go over, so this is first part, like a model done, save the model, everything done. Now for the next part, which is the transfer learn part. So let's see what we have in our paper. So on this part, we already trained the model and saved the model. That's good, that's done. And now we move to the next part. In the next part, as you can see, we have to use that model that is saved for the evacuation period. So to do that, what we do is that basically we have another combined model which pass all the like traffic related information, like the information that is generic, like the information that is valid for both regular period and also for evacuation period. These are pretty uniform. For example, the number of a detector or number of node do you have, then the total traffic that is changing over time, the traffic from different detectors, all this information are generic. Okay? So we pass this generic information into our train model that is saved, and from there we get an output. So this output is valuable, right? So why valuable? Because this output has this information about how the network is connected, how the network dynamics changes. Now we use this information at one end, and then in another end, since it's a special period, right? It's the evacuation period. So there will be some special things happening. There will be like a more traffic. So how the model will know that this is a special period? This has a more demand. So expect some weird behavior. So how the model is going to know? So to train that part, to train that model with that part, so we have some feature related to evacuation. So this feature is related to like number of population under evacuation, the distance from the evacuation zone to the hurricane landfall, and also some traffic features that is indicating like there is a demand change, significant demand change. So all this information is specific uh, for the evacuation period. Now we pass this information and then we use this information as a controller to extract like what type of information we should get from the regular period. So basically this is an controller that is trying to control and extract only valuable information from the regular period. Valuable information means like the information related to um, like a correlation between different traffic over different point of the network. Basically, the special correlation inside the network. Okay, so this information is extracted via this layer. And then finally, this information is used to get the final output for the evacuation period. Okay, so this final model, like the final code that we have, I will show you that, like how we do that. So this will give you the final forecast for the evacuation period. Now, as you can see, there are also an LSTM layer. As you know, like it will be always, it is always there, and it's always good that like whenever we have some temporal variation in the data, we use an LSTM layer to capture the temporal variation as well. So we did the same thing. Like although we have the input as a control layer, but we also have that input. Like these are also changing dynamically. So we also added this input to our LSTM layer to capture the dynamic temporal variation. Okay, so we haven't like so the idea is that we conceptually understand the problems, like understand the feature that are important for evacuation period, and we separately created like each block so that we extract all the important features. Either it could be temporal feature, either it could be special feature, either it could be the information from the regular traffic condition. All this information we extracted and finally combined to get the final uh, forecasted traffic. Okay, so this is the method that we applied for evacuation period. And why we applying that? Again, like evacuation happens for like a 7 or 6 days. You cannot train a model with the 7 days of data. So that's why we can only tune a model, right? So it's basically tuning the model, adding only important feature and giving it the best result. Okay, so now if we go back to the original code that we have, now the next thing is that this will be our new part. So basically, yes, we want to enable transfer learn. So we'll say just true. So this true part will enable transfer learn process. Okay, so now once we have the transfer learn process, now we'll go back in our main function, we run this code, and it says, hey, it's true, right? So it's true, then it will get again it will get the all the training information based on the input that you have provided. Now it's the evacuation period feature. So it will look into the evacuation data, and then it will split the data into training and test part, and then it will get the regular. Here you can see it is getting the regular model, what was already saved in some location. So it get that model, and then it deserialize the model to make it ready for next training. And then it's basically this model, once it's loaded, then next thing is basically we just pass this model to our combined model. So we are passing this model to combined model, and if we go back to this combined model, now you have the main combined model, which is basically using your information for both cases. Like the first is basically the PTR model, which is basically pre-trained model, and then we have the new model, which is using the new latest feature from the evacuation period. This is basically LSTM to learn the temporal variation. And this PTR model is just to basically learn the information from the regular traffic, that network informations, which is generic. Okay, so then finally, like we define all this information, we loaded all the model that we need. Then the forward step is the one where we will be starting like applying all those math, like do those math, apply those control layer. We have this information from the regular traffic. We use those regular traffic and convert it in the way that model can understand those. So convert it here, and then after those conversion, then again, like in LSTM model, just we defined in our final initialization part. So again, we are passing our input parameter, that input variables information that is needed for training the model. And then finally, we get the output from the evacuation period. And then we call our controller. And finally, call our controller. So now we have all the information that we need. We call our controller. And the controller means like it will delete some information and keep some information. So it's basically a binary, right? 0, 1, 0, 1. So that's why, as you can see here, with the controller is basically a sigmoid layer. So that's why it's a sigma function. And it will give you like either it's important or not important, something like that. So that way it will remove all the unnecessary information that is not required from the regular traffic, from the history. So now from the control layer, we have our output, and also we have the regular traffic information. So just control this part, like regular information from regular traffic, control this part, and add this information with our evacuation related informations, like a population or evacuation, and all those information. So all these things are already learned here. And then finally, we get our final output. So again, like there are some processing going on just to check out like what we need as the output. So we can, again, like it's if we have a more time step, then we have to pass the time step. Like we want to get the output as 7 hours, we have to provide the information that way. So all these things are parameterized. So based on your input, it will change the output. Okay, so now once we have this information, then finally we can go back our main layer. So basically our model is done. And we can use this model. Either we can save this model again. We can save this model. Like if save is true, then again, it will save the model, and we can use the model for our feature work, like either validating, testing, or directly if there is a system, like in the cloud, there is always a system, so we can deploy the model and you can use it for necessary work, like for understanding the network condition, network planning, everything. Yeah. Yeah, so this is mainly the two different types of model that we have here in our study to understand and forecast the traffic for future during evacuation period. Okay, so now I'll show you like what is the predicted values from the model and what is the impact of the transfer learning part that we have added and how our model is performing over the evacuation traffic. So here in the table, we already showed all the comparisons regarding like all the state of art model. Like we have the result of the prediction from LSTM model, then graph convolution LSTM model, then convolution LSTM model, then also like a dynamic graph convolution LSTM model, and our proposed one, dynamic graph convolution LSTM and the transfer learning graph convolution LSTM. So compared to if we compare that, as you can already see, the final one, the transfer learned graph convolution LSTM model, that actually performed the best to predict the future traffic compared to other models. And to deep dive into the results, like is if it's true that it's performing that well, so we have this comparison basically. So here we can see the comparison between the actual and forecast for and basically the correlation, how the correlation looked like between actual and forecast. If it's a perfect correlation, then it will show in a straight line. So now here, what is the correlation between is basically it's showing the correlation between the predicted traffic and actual traffic when we just use the model as it is. Like we train the model and apply the model for evacuation period. We did nothing, no transfer learning, nothing. Just bring the model, apply, and see how the prediction look like. As you can see, the prediction is pretty bad. Like it's very it's almost all over the places. It's supposed to be like a center toward this straight line. That way we can make sure that the actual and prediction is close, but it's all over the places. So that means it's not working very well. Like if we just train a model in a regular period and apply the model as it is, it will not work. And also here another figure also showing the same thing. It's very off. The blue one is showing the actual numbers, and the orange one is showing the predicted values. As you can see, it's pretty bad. And then we use this transfer learn model. Okay, so only use like a small amount of data to tune the model. Like we haven't done like we haven't started from zero. It's not like we started from zero training. What we did basically, we used this model that was trained for regular period, but instead of applying it directly, we did some tuning using a small amount of data. And then what it shows is that now the prediction is pretty good. We see the actual and prediction is pretty close and almost is it's basically moving around that straight line. And we can see the prediction and actual is pretty good. And also for here as well, you can see the transfer learn model output. The blue one again is showing the predicted, and the orange one is showing the orange one is showing the prediction and blue one is actual. So as you can see, the variations are well captured by the model just after doing that tweaking that we have done. And then we have also generated a overview about how the network look like. So this kind of information that the network planning team or emergency planner need, as you can see here, it's the predicted flows for different location. As you can see, the location near this is basically near Tampa, where the Hurricane Irma made its landfall. So here, as you can see, the density of traffic is pretty high. So this kind of information, if we can extract from the network well ahead of time, then now I can apply some strategy. Maybe I can say use the extra lanes or make the northbound traffic signals like a green time, increase that like maybe from 1 minute to make it like a 2 minutes, 3 minutes. So all these things can be applied just by looking and understanding what's going on in future and specifying like where the congestion is happening, where the problem is happening.
So in terms of future applications, we are thinking of a couple of applications. So once we finish this work, we actually move into multiple other extensions. So one of the things that we have been thinking about how we can improve the demand related data. So we were actually worked on another paper where we collected data from Facebook. So now after Hurricane Irma, there were a couple of hurricanes happened after that. And we collected information about Hurricane Ian, and we did an experiment with that. If we use data from Facebook, does it improve our prediction? And we found that if Facebook data from the movement from one location to another location, like how people are moving from different places, that actually improves our prediction certain percentage. So that is one of the things that we have done recently. Another thing, we are actually proposing to partner with Florida Department of Transportation that how we can practically use this model. And one of the application or use case of this model is that Florida uses emergency shoulder use for managing evacuation traffic. So what emergency shoulder use is that they open up one of the shoulder for increasing the capacity of the evacuation traffic. So what we are proposing that to utilize our model to understand when the congestion will be goes about a certain threshold, and then activate the emergency shoulder use. And we want to precisely say that where this congestion will be increased and when this congestion will be increased. So our model will give a predictive information to FDOT, and then the FDOT can utilize that information to precisely activate their emergency shoulder use the management strategy. So this would actually help them significantly. So this is at a proposal level. So we are not yet sure that whether they will be utilizing our tool. The third extension that we are thinking about is the transfer learning. So now we are thinking about how we can transfer one hurricane's traffic prediction to another hurricane. In one of the issues with this work is that we could not have multiple hurricanes data. So now we are experimenting with if we have multiple hurricanes data, that how we can make a prediction for one hurricane and utilize that knowledge to predict for a future hurricane. And the ultimate goal is that the model would be able to predict that future traffic for a completely unknown hurricane. And that's what we are aiming to achieve in our future work. So thank you very much.